Hi, in this screencast I'm going to give a tour of ZODB to help you decide whether you want to learn more. ZODB is a general-purpose, transactional Python object-oriented database designed to make working with persistent data as easy and transparent as practical. ZODB has a number of interesting features which we'll view in a bit, but first we'll look at working with ZODB by looking at a small web application. The application we'll use as an example is a two-tier Kanban board. The application supports a number of sites which contain a number of Kanban boards. The site used is determined by the domain used to access the application, dogfood@valuenator.com in this example. Boards are user selectable, and an organization using the application might have a board for each development team. Each board is used to manage features, which are units of value. A feature has a collection of development tasks. When a feature is dragged to a development state, a nested Kanban board is displayed to support management of development tasks. Features and tasks have data, which can be edited, of course. When features are completed, they can be dragged to the bag for archival. If we open the bag, we can see the most recently archived features, and we can also search for features based on feature and task text. To get a feel for working with objects, we'll access the database in an interactive Python session. The first step in accessing a database is getting a database connection. ZODB has a pluggable storage architecture, and the details of getting a connection vary depending on the storage approach used. This application uses NewtDB, which is a thin wrapper around ZODB that leverages a Postgres-based storage and also allows data to be accessed, indexed, and searched with PostgreSQL. We're using a Postgres database, and we create a connection using a Postgres connection string. We predefine the value of the connection string. To access the data, we start with the database root and walk objects from the root. If we print the root object, we'll see that it has a sites attribute. The root object is usually small and is used as an anchor for application-specific objects. The sites object is a mapping object that contains the sites by domain. Here we see the dog food domain that we're viewing in the example, as well as another one. Let's look at one of the sites. The site class is pretty simple. The site class subclass is persistent.persistent. User-defined class is stored in ZODB, typically subclass persistent, either directly or indirectly. Doing so causes them to have their own database records and provides logic for automatically loading the object if an attribute is accessed and marking an object to be saved if an attribute is changed. Site objects have a title and a collection of Kanban boards. They also have a changes object that tracks site changes. This is part of a real-time user interface framework that's pretty interesting, but we won't really have time to delve into it here. Another thing to notice about these site objects is that all of the attributes are either immutable objects like strings or mutable objects that are also persistent. A standard pattern when working with persistent objects is that their sub-objects should either be immutable or they should be persistent objects. It's possible to have mutable, non-persistent objects, but then the application has to take a little extra care because the changes to the sub-objects aren't managed by the database. Let's access a board. Boards have a number of interesting attributes, most notably the state and the tasks. The states attribute is, among other things, a sequence of states. If we look at the board, we see we have top-level states for the features as well as lower-level states for the tasks. And the states attribute contains information about the states. We can actually update the states for a board to reflect a particular development process. And so therefore the states are part of the data structure. The board also has tasks, which are the board tasks, or actually the board features and tasks. We don't manage tasks and features separately because tasks can be promoted to features and features can be demoted to tasks. So we use a single class and a single major data structure. There are some other data structures that supplement this a bit. Something to notice about both the site and the board class is that they look pretty much like regular Python classes. We don't really see database queries or database operations. There's little or no database code other than subclass and persistent. Note that we've accessed data by just accessing objects. We've been using attributes and keys and calling methods, but we haven't done any queries. If we look at the board site attribute, we see that it is, in fact, the site object. And again, this relationship between the board and the site, between the site and its boards, is represented as regular Python objects with attributes and mappings and such. The relationships between objects is managed by the database for us. We don't have to do joins. We don't have to arrange that the data are in the same database records. We just use them like we would use objects in memory. Let's add a feature to the board. We're going to do this by calling a method because the board has a number of bits of information that it manages about features, so we can't simply assign an attribute. And so we've updated, we've created a feature. We can see it has a title and so on, but we haven't actually changed the database yet. Any changes that we make are local until we commit a transaction. To commit a transaction, we'll import the transaction package, and we'll call the commit function. There are a number of variations on how this can be done, but we're just going to use the simplest mechanism here. Notice that when we committed the transaction, the new feature we added showed up in the board. Normally we'd have to reload the page, but the real-time API caused that to happen without requiring a reload. The most important feature here, though, is that, or the most important thing to note here is that the update was actually triggered by committing a transaction. Let's change the feature title. And again, nothing is saved to the database unless we commit a transaction. Now, suppose we decided this was a bad change, or perhaps we go on and make other changes and maybe there's an error. And so now we need to roll back all the changes we made. Well, that's very easy. All I have to do is abort the transaction. and the object's state is reverted to what it was before. When we abort a transaction, the data returned to the state they were at the start of the transaction. This feature, let's leave it at that. This feature of transactions is called atomicity. It's a wildly important feature of transactional databases. Without atomicity, recovering from errors is extremely difficult because it's up to the application to keep track of changes and unwind them. With a transactional database, the database takes care of that for you. I can't emphasize the importance of this enough. In the example so far, we've defined transactional boundaries manually. Lots of database applications are request-oriented, meaning the application does work in discrete units. For these applications, the application framework will often manage transactions. In this particular application, we've configured the web framework to automatically begin transactions at the beginning of a web request, to commit them when the request succeeds, or to roll them back if there's an error. Let's look at the REST API for updating a task. The details of the web framework aren't really important. This update task endpoint simply calls the application code for updating a task and takes care of web-specific details. And then we can look at the application method that it calls, and this is a pretty clean method. It gets a task and it updates its data. It also calls into this framework for real-time UI, but there really isn't any database code here. When we called self-task change, that isn't a database operation, that's an application level operation. We didn't have to set a transaction boundary. We didn't do any other kind of query other than looking up the tasks. So far, we haven't seen any obvious database queries. We simply traversed objects. When we accessed a board by name, that was a kind of a query. The collections of boards and sites, as well as some other collections used in the application, use B-trees rather than ordinary dictionaries. B-trees are very efficient for working with large mapping objects with ordered keys. They can spread data over multiple database records, so very large collections can be handled without loading the entire collection into memory to access a subset of keys. This application doesn't need search beyond mapping access except in an important case, which is searching the bag. In ZODB, search is viewed as something to be provided at the application level. Most commonly, catalog objects are used. These provide application-level search engines built on B-trees and possibly other data structures. There are a variety of these to select from. Because of ZODB's powerful caching, catalogs are often faster than using external indexes like Postgres or Elasticsearch. In this application, we leverage Postgres for search. NukeDB replicates object data to a Postgres JSON-B column, and the application uses a Postgres full-text index to support task search in the bag. Now that you've seen ZODB in action, let's review some of its notable features. First of all, ZODB is transactional. Transactional databases are often characterized by a property called ACID, which summarizes atomicity, which we've talked about, consistency, which we'll come back to in a bit, isolation, meaning that different transactions can be running at the same time without interfering with one another. This provides a powerful concurrency control mechanism for data-centric applications. And finally, durability, which of course you'd expect from a data storage mechanism. Transactional semantics should not be sacrificed lightly, although many applications do, I think at their peril. A major feature of ZODB is caching. ZODB provides a fairly aggressive caching as part of its effort to provide transparent persistence. The ZODB object cache is an in-memory object graph. We saw that when we accessed objects, we simply accessed object attributes, and that was accessing cached values in some cases. In some cases, it was causing data to be loaded from the database transparently to us. The object cache is transactionally consistent, and it's a partial database replica. What this means is that we don't have to worry about whether our data are stale. Anytime we begin a transaction, the cache is caused to be consistent with the database as of the beginning of the transaction. And then, of course, the cache is only changed through application actions. ZODB has a pluggable storage architecture. This provides a lot of flexibility in terms of application requirements and has also allowed various developers to provide value by developing special kinds of storages. A number of sort of basic storage options are available, including a file-based storage, which is useful for embedded databases, and in-memory storage, or a couple of in-memory storage that are useful for testing. There are multiple client-server storages, and a relational database storage that allows storage of data in Postgres, Oracle, or MySQL. There are also storages that layer on top of other storages to provide things like compression, data encryption, testing, and even replication. ZODB provides really great testing support. First of all, because application logic is usually completely devoid of application code, the application code can be tested, especially unit tested, without any database being around. In those cases where we want to look at how application objects interact through the database, we can use an in-memory storage. There's a kind of storage called a demo storage, which uses an in-memory storage for changes on top of an unchanging base storage, which can also be a memory storage. Tests that need a common base database that's non-empty can, as part of test setup for a package or a collection of tests, create a base storage, typically in memory, and then each test can layer a demo storage on top of that, which is then tossed at the end of the test when it's torn down. This allows you to test database code without having to have a database server or to manage database files. ZODB provides blobs, which are a form of database managed files. They're used for large opaque data like media or perhaps specialized data files. When a blob is opened, a file object is returned. If a blob is open for write, then a copy of the previous value of the blob is created, and then changes are made against that copy. Blobs can be used with either a network file system of some sort or with a server and a local cache. ZODB provides garbage collection. One of the most interesting problems in database design is referential integrity, and in fact, relational databases provide integrity constraints that error if a application removes a record that's referenced by some other record. In ZODB, applications don't remove records. Periodically, ZODB runs a garbage collector, and any database objects that are no longer reachable from the root object are removed from the database automatically. You could argue that requiring database or applications to manage referential integrity is a little bit like asking them to manage memory and avoid null pointer errors. ZODB works with the transaction package to provide distributed transaction support. This allows ZODB to be integrated with other transactional databases in such a way that they coordinate their transactions so that you can make changes across multiple databases and know that the changes are going to be consistent. Many modern databases, especially NoSQL databases, claim to be schemaless. but really there's always a schema. It just may not be actually stored in the database. Like many NoSQL databases, ZODB doesn't store schemas in the database. Schema management is an application concern, and schemas are typically expressed as Python classes, but they can also reflect other application logic. The point being here is that they're completely independent of the database itself. You may want schemas to help provide application level integrity. For example, you might have a schema that restricts the attributes of an object to a certain set of names with a certain set of types. You can still do that. You would simply use one of a variety of application level schema frameworks. There are also migration patterns in ZODB. Many schema changes can be made very easily. For example, one of the most common is to add an attribute to a class. To do that, all you really need to do, or add an attribute to database objects. To do that, all you have to do in many cases is add an attribute to the class. And then any existing records will get a default value from the class, and so don't have to be modified as part of a migration. There are also migration frameworks that help when migrations do actually require changes to database objects. You might wonder if ZODB is a NoSQL database since it doesn't use SQL, but really NoSQL databases generally have a different set of concerns than ZODB. They're often geared towards being able to write data as quickly as possible, which is especially important when collecting real-time data from the environment in some fashion. They emphasize write speed, and to get greater write speed as well as greater availability through distribution, they typically sacrifice transactions. They mitigate the loss of transactions by supporting complex schemas or documents. So they avoid any need for joins, and they allow values to be inserted or allow complex values to be inserted with a single request. Updates are still sort of problematic. If you imagine an application reading a value, computing a new value, and then saving it, some other application might have read that value and saved it in the interim. And if so, that other application save will be lost because there aren't transactions, and so there's no real connection between reading the value and saving it unless the application provides some safeguards. In general, the notion of consistency in NoSQL databases is entirely different. Typically, these databases which provide distribution as well as speed are viewed as consistent if the value for a particular ID is the same across all the different nodes that store it. Whereas the notion of consistency in a transactional database is that the values in the database are consistent across IDs that are consistent with each other, where consistency is defined by application logic and rules. And the database doesn't undermine that in any way. And this is related to isolation, and in general, the notion that the state of the database is a state that could have been achieved by applying transactions in sequence. But the high-level idea there is that the values across records are consistent. It's not enough that the values are consistently stored across nodes in the network. ZODB is somewhat optimized for reads. Really, a better way of saying that is that ZODB is optimized for usability, and the cache is a core part of that. Because of the ZODB object cache, reads are often extremely fast. They're basically as fast as normal memory accesses. ZODB is a little bit slower at writing than many relational databases, which are typically slower than some NoSQL databases. But having said that, ZODB can still write thousands of transactions per second, which is fast enough for most applications. So in summary, ZODB was designed to be very easy to use, to provide a very transparent persistence model, to make developing persistent objects as easy as working with objects in memory. It's transactional. It provides consistent caching. which provides a lot of performance as well as helps to provide integrity because you don't have to worry about cache invalidation. Provides very easy testing, both because lots of application code doesn't have any database code in it, and also because it's very easy to work with in-memory databases. It provides garbage collection so that you don't have to manage referential integrity yourself, and it provides database managed files. To learn more and to work through a tutorial, see ZODB.org. Thank you very much for your time. Bye-bye.